Hello, and welcome to the last video for the semester. Number 66 from chapter 38 will be a great excuse to go through all the details in Bohr's solution for the hydrogen atom. I think this was around somewhere between 1905 and 1915. This is where people still conceptualized the atom as a little tiny solar system before Schrodinger came along in like 1920, thereabouts, plus or minus 5 years of 1920. And brought the full force of the so-called Schrodinger equation to bear on the atom and did a really awesome job of predicting the spectrum of the atom. But surprisingly, this simple model from 100 years ago, more than 100 years ago now, accurately predicts many features of the hydrogen atom's spectrum. Those are the colors that come out of the atom. So I find this very exciting. If you don't find it exciting, it's because you're probably not thinking about what you're doing as you do it. You're just trying to get through the semester, and I totally get that, but maybe you'll reflect on it later, how material that you learned maybe in 3B, 3A, some of the stuff we did this semester, it all comes together and allows you to, with very little math, explain the colors that come out of an atom. And that's insane because you can't see atoms. They're too small. And yet you can probe their structure with your mind and math. Okay, so let's review some preliminaries. The mutual electrostatic, I'll say electric potential energy of 2 point charges. In our case, it's going to be a plus and a minus charge. We'll say they're separated by a distance r. We use the letter U for potential energy. Here it is. It's K Q1 Q2 over R. That's it. It's much like the gravitational potential energy of 2-point masses. I know all of you took 3A and you learned about gravitational potential energy. There was a minus sign in front for gravity because gravity is attractive. And then you had a big G here instead of a K. Product of the charges, or excuse me, it was the product of the masses for gravity and inversely proportional to the distance between them. Now, here, when we're talking about electric potential energy, it could be attractive as it would be for these two. And if that's the case, one of these charges is a negative number, and you still get the characteristic negative 1 over R shaped potential energy for their interaction. If both charges are positive, there's a repulsion here. These are both positive, and you would get a graph that looks like this, flipped onto the other side of the r-axis. It's not supposed to touch the r-axis there. And K is defined as, so the way your book does it in 3B, if you took 3B, they prefer to actually write K as 1 over 4 pi epsilon naught. Which of these you use is a matter of convenience, really. In some problems, in some integrations in 3B, this ends up being more convenient actually than K, but you should just know that K has a value of basically 9 billion, 9 times 10 to the 9th. And the units, I forget, it's probably Newton meters squared per Coulomb squared. It basically describes the strength of the interaction between two charges. It's a really big number because there's a tremendous force between two charges at a distance from each other. The force between them is much greater than the force of gravitational attraction if they have mass. All right, what else do we need to know here? How about the force between charges? This is known as Coulomb's law. Everybody who took 3B would know about it. It's just like Newton's law of gravity, except the force is proportional to the product of the mass, the product of the charges this time, not the masses, but it's still an inverse square law. It looks identical to Newton's law of gravity, but we've got a different constant describing the strength of the interaction. So I should really emphasize this K has nothing to do with Boltzmann's constant. This is not the K in 3/2 KT, not at all. Different K, no relation whatsoever. That's probably why your book chooses not to use it, because K gets abused. Used and abused. Spring constant, electrostatic interaction, Boltzmann's constant, probably other things as well. Okay, I'm going to do it this way because in the derivation of the Bohr atom, it saves a little bit of space. That's why I'm doing it. Later, we'll go back and substitute. Okay. And what other facts do we need? The mass of an electron. I believe it's 9.1 times 10 to the negative 31st. Sometimes I'm embarrassed for knowing these numbers because it's trivial. You know, you could just look them up, but you see it enough times and it sticks. The charge on an electron, we call that the fundamental electron charge, or the fundamental unit of charge. It's that 1.6 times 10 to the negative 19th coulombs. We're also going to need the value of an electron volt. This is a unit of energy, but in SI units, well, that would be an electron is 1.6 times 10 to the negative 19 coulombs times 1 volt. Well, a coulomb volt is a joule. So we're talking about 1.6 times 10 to the negative 19th coulomb joules. In other words, 1.6 times 10 to the negative 19th joules. So that makes that easy to memorize. If you can memorize the charge on an electron in SI units, then you also know the value of the electron volt, which is energy in SI units. And that tells us that Planck's constant is 6.626, don't really need all those digits, times 10 to the negative 34th joule seconds. But now I've established that 1 joule is equivalent to 1.6 times 10 to the negative 19th evolts. So I can get rid of the joules and express H in evolt seconds, which is really useful. 6.626 10 to the negative 13th, or negative 34, excuse me. What have I done wrong there? That's not right. Rookie mistake. I know you're judging me. It's 1 electron volt for every 1.6 times 10 to the negative 19th joules. So I had the units in the correct position, but I had my conversion factor upside down. Excuse me. Okay, divide by 1.6 e negative 19. What am I doing wrong here? I'm going to pause and get this right. This number is also in your book. 4.14 times 10 to the negative 15th evolt seconds. And I would like to take this opportunity to say a word about this value of H. I probably shouldn't have put the units in parentheses. Remember this Planck-Einstein formula, the very simple formula that tells you the energy of each packet of light if you know the frequency of your electromagnetic wave? Well, don't we measure frequency in hertz? And hertz is just inverse seconds. Like if something happens 1,000 times per second, the units are per second, inverse seconds. So if energy is going to come out and what we're plugging in for the photon is hertz, then this should really be joules per hertz or evolts per hertz. And that's really what it is. It's evolts per hertz. Evolts per inverse seconds, because inverse second in the denominator is seconds up top. Now, the number itself is extraordinarily small, but just suppose that Planck's constant was 10 joules per hertz. That would mean for every hertz of frequency, for every cycle per second in your frequency, your photon would have 10 joules. So if your photon had a frequency of 13 hertz times 10 joules for every hertz would mean 130 joules for every photon. Now that's a ridiculous number because photons are extremely tiny. No photon has 130 joules of energy. That's just impossible. I've never encountered that even in astronomy. So it's a much smaller number, but that's how that works. You can think of an evolt second as an evolt per hertz. Now h bar, that's h over 2 pi. It shows up so often in modern physics that it's useful to write it h bar. Got to be down with the h bar. And 4.14 divided by 2 divided by pi gives us, oh, no, that doesn't look right either. Why does that look so small? Oh, right. They usually move the decimal place over. So 4.14 e negative 15. Now I'll divide that by 2 pi. And, okay, so I'm making another mistake. What's going wrong here? Okay, I realized I'm unaccustomed actually to seeing h bar in evolt seconds. I am accustomed to seeing h bar in joule seconds. So if you take the SI value of h and divide by 2 pi, you get this familiar, for me, familiar 1.05 times 10 to the negative 34 joule seconds. This is going to come up a lot, so I'll put this off to the side. We're going to use all these fun facts towards the end, and throw those on your note card. You can fit them. And now, let's proceed with the problem. There's a lot to do here, because as I mentioned, we're going to do this from the very beginning. Rather than quoting the formulas, let's do everything from first principles, and to that purpose, we need to take a look at a box of formulas in your book. So your book develops the formulas for the hydrogen atom strictly. That's a single electron orbiting a single proton. But then they explain how you can change the nucleus, and the formulas are very easy to adapt. So what's the next? Helium. Helium's the very next element. Let's say you're talking about regular old helium, which has 4 nucleons, 2 protons, 2 neutrons. If helium has been ionized, normally helium has 2 electrons, 2 protons. If you take away one of the electrons, you have a single electron orbiting this helium nucleus, which looks just like the hydrogen atom. The only difference is the difference in the charge at the core. So if that's the case, if you have a so-called hydrogen-like atom with a single electron orbiting a nucleus, all you have to do is adapt the hydrogen atom formulas to your hydrogen-like atom. And that's what this capital Z is for. Capital Z is the number of protons, the atomic number, in the nucleus. For hydrogen, it's 1. So if you plug in Z equals 1, all of these reduce to the formulas derived in the book. But these formulas allow you to make an easy fix for a hydrogen-like atom. But truthfully, what I'll probably ask you to do on the exam is just start the process from the beginning. Because what's the point of just quoting these formulas? You haven't really learned a whole lot. And it's really not that bad anyway. And I'll make the rest of the exam not too long to compensate. So that's what we're going to do here. In fact, this problem, number 66, has 2 complications. First of all, the quote electron, because it's actually not an electron, is orbiting a carbon nucleus, which has 6 protons. So we do have to use the Z here. But also we're told that it's a muon orbiting the nucleus, not an electron. A muon has the same charge as an electron, but it's considerably more massive. So rather than, it's actually, I think, more difficult to try to sort out how to fix all these formulas to account for the different nuclear charge and the different mass of the orbiting particle. That's more difficult than to just do it from the beginning. So forget all these stupid formulas. Let's just start from the basics here, and we'll get right into it. Oh, I thought I paused, didn't pause. Okay. So here we are. You know what? We need to look at a graphic from the book. This nice little graphic represents the electron, or in this case, the muon, existing as a matter wave in the circumference around the nucleus of the atom. So they haven't drawn the nucleus of the atom here, but it's supposed to be there at the center. And it's a very modern idea. Well, not so modern now, but it was a strange idea around the year 1900. Remember de Broglie? He was the first to suggest that, hey, if electrons can exhibit this duality, this wave-particle duality, then why not the same for material particles like the electron? We typically think of the electron as a little bundle of mass. It's like a little ping pong ball, but super small, flying through the air in some definite direction, like with a definite speed. De Broglie was the one to suggest that maybe that's not the entire picture. Maybe this particle can also behave like a wave. Now, we've spent so much time at the beginning of the semester talking about interference and standing waves, so you really should review the simpler problem in chapter 38, the particle in a box. If you put a single particle in a one-dimensional box, you can imagine it bouncing back and forth. Well, if it's moving back and forth as a wave, it could possibly destroy itself, in a manner of speaking, due to destructive interference. So if there's any hope of having a standing wave, because the modern interpretation, which materialized in the 1920s or 30s, is that the amplitude of this wave is related to the probability of the particle existing at that point in space. So if you get destructive interference everywhere so that the amplitude is 0, then you've got no existence of the particle. So we need constructive interference, and you argue that the length of the tube or the box has to be an integer number of half wavelengths, right? This is 1 hump, which is a half wavelength. 3 humps is 3 halves of a wavelength. Those are the conditions for constructive interference. It's just like those standing wave resonant modes in a trombone that we talked about for acoustic standing waves or standing waves on a string. Exact same mathematics. But now we're doing it around a circle. So granted, it was realized or discovered by the 1920s or so. I forget which year exactly Schrödinger published his paper, but now we know this is still a rather naive picture, but it's way more accurate than the Rutherford atom, which is just a solar system. So we're going to argue that the circumference of the orbit has got to be an integer number of half wavelengths. That's the wave stipulation on this particle. And that's a foreign notion because if you go back to gravity and planets orbiting the sun, there's no restriction on how far out you can put a satellite. Like SpaceX, they can put a satellite in orbit around the Earth at any radius they want. There doesn't appear to be any restriction there. Well, when you get down to the level of the atom, it turns out to be quantized. There's that fancy word. Only specific orbits are allowed, and that's what we're going to see in a moment. And one reason for that stipulation is this requirement of constructive interference. So let's make the argument now on paper that the circumference, 2 pi r, has to be some integer number of, oh, you know what? It was full wavelengths this time. Yeah, it's got to be full wavelengths. Otherwise, you would actually have destructive interference. Does that make sense? So this picture, in a way, is misleading, is it not? Because it looks like you've got a downward oscillation canceling an upward oscillation. Oscillation of what? Like I said, it's probability, amplitude. We don't have time to talk too much about it, but the requirement is actually that it's an integer number of wavelengths, so that when it gets back to where it was, it's already retracing its steps, right? Because in the tube, the round trip distance is actually there and back. That's what it was. It goes here, bounces back, and then needs to retrace its steps. But here, the round trip simply is the circumference. Okay, so we're ready to continue. Stop share. Okay. So the wave requirement says that the circumference must be an integer number of wavelengths, not half wavelengths, full wavelengths. And then we use the de Broglie relation. So we couldn't have done this without de Broglie's contribution. The wavelength, we know, is Planck's constant, not h bar, but the actual h, over the momentum. Remember that? De Broglie borrowed this from special relativity. He said if it's true for photons, maybe it also works for material particles. Classically, the momentum is mv. So look, we're already mixing classical and quantum ideas. We're making a requirement on the wave nature of, or wave behavior of this particle, but we're borrowing a formula from classical mechanics for the momentum of the particle. It's very, I never cease to be amazed by how weird it is that this even works. Because when you have time to really think about the stuff, you end up wondering, does this stuff even work? Like, they're just grabbing at stuff. That's what it feels like. They're just taking random guesses, and patching stuff together. Well, the ultimate proof is in the experiment. This model, believe it or not, correctly predicts the colors emitted by the hydrogen atom. Now, like I said, within a few short years, a more mature theory evolved, and it just gets more and more more and more fleshed out, more rigorous. It's really a sight to behold how the whole edifice of the quantum theory was built up over these years and decades. Okay, so let's make that substitution in here. Instead of wavelength, I'll write h over mv, and we're already making progress. We've got one relation already that relates the radius and the speed. There's a constraint there. If you think back to Kepler's laws, 3a, hopefully you remember that a satellite going around the sun, could be an asteroid or a planet, at a specific distance from the sun, if you'd like that thing to be in a circular orbit, there's only one speed at which you can orbit. So the distance determines the speed, and we've got a similar condition here. So what I'm going to do is take the 2 pi, put it over here, and then rewrite h over 2 pi as h bar, and I've got this requirement. Should I do it that way? I can also swap v and r. I think I'll do that. So v is equal to n times h bar over m r. Let me put a box around that. All I did was move some stuff around and absorb the 2 pi into h bar. So this is our first restriction on how speed and radius relate. It's not the same restriction that we saw in Kepler's laws and gravitational orbits, but now we are going to see the same restriction from classical mechanics for gravity orbits, but this time we're talking about orbits due to an electrical force. Okay, so think about your nucleus. In this problem, it's that carbon nucleus. I'm just going to draw my little bunch of grapes. Some of these are positive, some are negative. And now we'll go back to the naive solar system picture of the orbit, where it's just like a planet going around the sun, but the source of the centripetal acceleration is the electrostatic. It's not really electrostatics, it's the electrical attraction between these two. That's what keeps this thing accelerating. So instead of just continuing to move tangentially, well, or I should say to the left, it's going to accelerate. It'll deflect because of the central or centripetal attraction. Again, you know, which picture is correct? A moment ago, we're talking about a standing wave around a circle. Now we're talking about a particle moving like a planet. You know, what gives? It's like you need both. And you may have read the historical note that the way we're going about it here is not really what Bohr did. Bohr had a more, what's the word I'm looking for? Circuitous, meandering line of thought. I've never actually read his original paper, but he borrowed a lot from the advanced classical theory of planetary orbits, as I understand it. Also, he was financed by beer. He was part of a Dutch family, no, Danish family that made a lot of money off of a brewery. So, and that's not the only example in math and science. The student T distribution from statistics, also financed by beer, financed by the Guinness company, because some guy was looking through a microscope and thinking about, he was doing quality control by counting yeast cells, and he started thinking about sample versus population, and he actually advanced the field of statistics during his time at Guinness, but he wasn't allowed to take credit for it because he was a company employee, so they called him student instead of whatever his actual name is. How sad is that? Don't know his name. Okay. I really hope you remember this from classical mechanics. You can apply Newton's second law along the r-axis. That's the axis that points towards the center. It says the sum of the forces along the r-axis is mass times centripetal acceleration. If you really are moving in a circle, so your radius isn't changing, then the centripetal acceleration can be calculated as speed squared around the circle over the radius, v squared over r. I'm sure you've all seen that. And now we use Coulomb's law, the force between them. Well, here's where we have to recognize that this, usually it's an electron. In this problem, it's a muon. In either case, they have the same charge. It's the fundamental charge E. Now this thing has Z as in zebra, Z protons, and then some extra neutrons. So the total charge here would be Z times the fundamental charge. So this is Q1, this is Q2 in Coulomb's law. Here's the force, it's K, ZE times E, or Z E squared. I've written the product of the charges. Pardon me. And it's an inverse square law, just like gravity. So all we've done is apply Newton's, see? Newton's mechanics. Also, we got Coulomb's law, Newton's mechanics, this modern idea that particles are waves. All the ingredients are coming together. And I would like to solve this for v squared, because I'm going to compare it to what this says v squared should equal. So let's move some stuff around. I'll put the r over here. This r cancels one of those r's, right? Yeah. And this m will go over here. And I find that v squared needs to be k z e squared over rm. I believe I did that correctly. Let's check everything here. As you're going through this, be as careful as possible and write neatly so that you can refer back to your results. Like I said, I really think this is easier than trying to make corrections to all those formulas. Okay, well, we've got two conditions now on how speed and radius relate. You can't just pick any old radius and have any old corresponding speed. Both of these must be satisfied. So if I square this equation, I get v squared equals n squared h bar squared over m squared r squared. And that's two simultaneous restrictions on the value of v squared. So why don't we take this and set them equal to each other? If they're both equal to v squared, then they're equal to each other. So kz E squared over Rm equals h bar squared over m squared r squared. And what have we done here? Do you see that speed has been eliminated? Wait, did I drop the n squared? I did. That's important. Speed has been eliminated. So we've got a single formula on the allowable values of r. Remember, what's the restriction on n? What are the possible values taken by n? It's got to be an integer. 1, 2, 3, etc. 0 is no good. Otherwise, you'd have no waves around your circumference. So evidently, we've already determined that r, the radius, or the radii, the possible radii of the orbits, are discrete. I guess you could say quantized as well. That word gets used for different things. But there aren't just any old allowable orbits. The electron of the hydrogen atom, or your hydrogen-like atom, can only occupy a discrete set of orbits, which is a radical new idea. And you should be reading about the Bohr atom versus the Bohr hydrogen atom. Bohr had a model for atoms generally about how there's discrete energy levels, and when an electron jumps between levels, it emits or absorbs a photon, a packet of energy. That's true for all atoms, but we're looking specifically at the hydrogen atom, where he was able to predict the energy level. So that's really the only difference, is that for hydrogen, he went as far as calculating the spectrum, calculating the possible energy levels. So let's solve for r. If I put r squared over here, that would cancel the r downstairs. And it looks like, and I'm now going to label r with the subscript n, because r takes on specific values depending on the integer value of n. So we've got n squared times, and everything that's not n squared, I'll put in parentheses. What do I have? Well, this n is going to cancel one of those n's. And it looks like I just have h bar squared over z times m, I'm really trying to be careful here, k e squared. That looks familiar. I believe I did that correctly. Let me check my notes from earlier today. Let's just run with it. Here, I'll pause and take one last look at my work here. Looks good to me. Now here's what your book likes to do. For hydrogen, Z takes on the value 1 because there's only a single proton in the nucleus. M is the mass of the electron. And then remember, K is really the reciprocal of 4 pi epsilon. And in case you're wondering, or if you've forgotten what epsilon naught has to do with, again, that also has to do with the strength of the interaction between electric charges in a vacuum. They call it the permittivity of free space. It showed up in our calculation of the speed of light back in chapter 31. So they put K as a 4 pi epsilon upstairs, and then they actually evaluate all of this, and they call it the Bohr radius. So they would say R sub n is equal to n squared times A. I think they put a B for Niels Bohr. And this number ends up being about half of an angstrom, 0.5 angstrom. Angstrom is a popular unit of distance in astronomy. It means 10 to the negative 10th meters. That's a tenth of a nanometer. And I have that number memorized because it just shows up all over the place. The very smallest atoms are about 1 angstrom in diameter. That's half an angstrom in radius. That is the very famous Bohr radius. And you know what's really weird? When you use the Schrodinger equation to calculate the energy spectrum of the hydrogen atom in a much more sophisticated manner, we're talking like hours more calculation, you end up with the same distance. You end up describing the electron as a probability cloud, and you look at where the probability is most dense, and it turns out to be most dense at the Bohr radius. It's so weird because it's a totally different starting point, and you wind up with the same result. Anyway, so we could come up with some cute abbreviation here, but this Bohr radius is different because we're going to have a Z of 6 in this problem because our nucleus is a carbon nucleus, 6 protons, and the orbiting particle is not an electron, it's a muon, so we'd have a different mass. I'm not even going to bother to call it a Bohr radius or anything like that because we're just doing it for this particular problem. So I will put a box around this. And if I wanted, I could evaluate this right now to see how all of the radii compare to that basic radii. Notice when you plug in n equals 1, that's the very first radius. 1 squared is 1. That means that this quantity in parentheses is the very first radius. And then the radii get bigger after that, because for n equals 2, this is 4. So the next radii, or next radius up, is 4 times, or I should say the next orbit is 4 times in diameter the innermost orbit, and then you've got 9 times for n equals 3. You get the idea. So we'll save that. Now, what is the problem actually asking us for in number 6? Because I suppose we could do everything that they're asking for, and we're doing it in a different way than the solutions manual, because we're starting from the very beginning. It's really not that bad. Part A, what are the orbital radius and speed in the n equals 1 state? Yeah, you know what? Let's just find the formula. I'm not worried about the absolute, the numbers in SI units. Now that we know the radius, we can go back here to the expression for speed. We could really plug in our expression for R to either equation and get the same result. Remember, that's what we did. We solved 2 equations for 2 unknowns. Let's use this one because it's easier. So the nth speed would be n times h bar over m. See how it's really, it's h bar over mr. So dividing by r is the same as multiplying by the reciprocal of r. So all I'm going to do is multiply by the reciprocal of all this. That would be my way of dividing by r. So that would give me a z mke squared over n squared h bar squared. Okay, one of the h bars here gets canceled by that one. And that's interesting that the masses go away. And also one of the n's down here gets canceled by that one. So I'll get rid of that, I'll get rid of this. And v sub n is 1 over n times, we're left with z ke squared over h bar. So evidently, if you plug in n equals 1 here, v sub 1 is just this junk in parentheses. So this is what you could call v sub 1. This is the speed of your muon, or whatever your particle is, orbiting particle, in the innermost orbit. So I could say v sub n is equal to just v1 over n. And your book has a formula just like this at the end, specifically for the hydrogen atom. You can just express all the speeds as the lowest speed, or the highest speed really. The innermost orbit has the highest speed divided down by that integer there. By the way, n is called the quantum number for your hydrogen-like atom, which is kind of a cool phrase, the quantum number. It tells you, once you know the quantum number, you know the radius of the orbit, you know the speed, you know the energy, etc. Okay. Where do we go next? Yeah, so again, if you try to compare this with what's in the book, I think they try to do something succinct, like write this in terms of the Bohr radius. I don't think it's really worth the effort for this problem. So I'll put another box here. And let's go one step further. Let's find the square of the nth speed, because when we go to calculate the energy, we need the kinetic energy. That involves v squared. So this is 1 over n squared, z squared, k squared, e to the 4th over h bar squared. I'm putting boxes around these to make it easier for me to locate it in a minute when we have to calculate the energy. Okay, so they asked, in part A, they asked for the radius of the orbit and the speed of the muon in its ground state. That's the n equals 1 state, innermost orbit where it's moving the fastest. I'm not going to do that. All you'd have to do is plug in numbers. That's a little tedious. Okay, now they're asking for the wavelength of the 2-to-1 transition. So the wavelength of the 2-to-1 transition. So remember, there's this little graphic you should be aware of for these hydrogen-like atoms. Really any atom. It's got a discrete ladder of allowable energy levels. And these ladders exist for each electron. Remember, a multi-electron atom, each electron can occupy various shells, various energy levels. Now you're talking about filling out the periodic table. You know, Pauli exclusion principle, you can't have two electrons in the same state. And, you know, you could have two electrons in the same subshell, like 3D or 3S, but they have different spin, so they're not really in the same energy level. It gets complicated, but this is really the starting point for all of that stuff. So you'd have the lowest energy level, the ground state, the next excited level, E3, etc. And you can have an electron, or in this case, a muon, absorb a photon while in the ground state and be bumped up to an excited state, or it could already be in an excited state and fall back down. And something you should know, you should just briefly review emission versus absorption spectra. Absorption, especially those of you who are going to study astronomy. You're going to use all this stuff. It's so cool. Everything we know about stars is from the light that we receive from the stars. And it's all quantum mechanics. It's all applied this stuff. So in an absorption spectrum, you've got a quantity of like cool gas, let's say, cool helium atoms. And because they're low temperature, all of their electrons tend to be in the ground state. And so the only possible transitions you can get would be things like getting boosted up to the E2 state, or boosted up from 1 to 3. These are the allowable transitions. So the only photons that will be absorbed are the ones whose energy matches these transitions. You're not going to see this photon missing from the absorption spectrum because these photons don't get absorbed. You would have to have a bunch of electrons already in the E3 state in order to experience this transition as your cool gas is being illuminated by light from somewhere else. That's what an absorption spectrum is. Like the atmosphere of the sun has a bunch of lower temperature gases that are at a much lower density than the surface of the sun. So the light being emitted, the black body radiation coming from the surface of the sun has to pass through the sun's atmosphere. And the atoms in the atmosphere, let's just for now, it's more complicated than that, but let's say that they all have their atoms in their ground state. And so they undergo absorption, and some of the colors are missing as a result. The light that you receive from the sun has some colors missing. You should just look up the sun's absorption spectrum and you can see it. It's a rainbow with black vertical lines indicating the colors that are missing. Okay, so we're supposed to figure out what is the wavelength of the 2-to-1 muon transition. That's easy. So if the muon were in its E2 excited state and it fell back down to the ground state, what's the wavelength going to be? All that means is we just have to find the energy levels, because once we know the energy levels, the difference between them can be calculated. I'll call this 1 to 2, 2, 1. It really doesn't matter. And then we use the the Planck-Einstein relation, that the energy of a photon is equal to HF. Well, we know that frequency, remember this result, the speed of a wave is wavelength times frequency. So frequency can be written speed of light over lambda, and that's why you can rewrite the energy of a photon in terms of its wavelength. I kind of like doing it that way better. And that means you can solve for the wavelength hc over E. So all we have to do is figure out the difference in these two energy levels, and that would correspond, or that would equal the energy given off in the form of a photon, right? Conservation of energy, when your muon jumps back down, it loses energy. It gives that energy up to a little photon that goes off into space. The squiggle indicates a photon. That's the energy of the photon right here. We just plug it in, and we can solve for the wavelength associated with that transition. It's like, no, it's a mystery solved around the year 1900. People didn't understand why atoms gave off discrete spectra. So what we're really doing is finding the energy levels. That's it. And most of the work is done. All that's left is some algebra. Okay, back to our silly classical model. That's what's so amazing, is the classical stuff still works. All those hundreds of years of physics, it's not like you throw them all out. You don't throw the baby out with the bathwater. I don't know where that expression comes from. The baby's still in the bathwater. The total mechanical energy of your muon or electron as it orbits the nucleus is the sum of kinetic and potential energies. And we're doing this in 3A right now. And here we are still using it to explain atoms. Well, it's got kinetic energy of 1/2 mv squared. Now, this is a classical model. If the muon approached the speed of light, this would not be sufficiently accurate. And then the potential energy is, this is where we're going to use some of the preliminary results. This is the mutual potential energy of a pair of electric charges. But now, remember, one of the charges is, here's my little graphic. One of the charges in this formula is the nuclear charge, Z protons times E per proton. And then Q2 is negative E. The muon is negatively charged. It has to be, right? You have to have an attraction between the two if you've got an orbit. So that's why we pick up a minus sign, minus K ZE for one charge, E for the, well, negative E, the minus sign's over here, for the other, divided by, not R squared, that's an easy mistake to make. Force is inverse square. Potential energy is 1/r. And that's it. Now, I haven't written the subscript n yet, but remember, we've only got certain allowable radii, and which radius you're talking about depends on the quantum number n. Once you specify the quantum number n, you're talking about a specific radius, r sub n, and you're also talking about a specific speed that matches that radius, and that means you're talking about a specific energy. Yay! We've already shown that the energy levels are discrete. There's a ladder of allowable energy levels. So let's go plug your stuff back in. So do you see now how it's really not that bad? If you were organized, better than me hopefully, I've already got my expressions for r sub n and even v sub n squared. All I have to do is plug them in. I think this is easier than trying to fix the Bohr or the hydrogen atom formulas. 1/2 m, don't forget, this is the mass of the muon in this problem. It's whatever particle you're talking about that's orbiting the atom. If the premise of the problem is that a muon was captured, they give you some background on what a muon is. It comes from outer space. That sounds like a science fiction movie. It comes from outer space, gets captured by atoms, and because it's pulled really close to the nucleus, it's like within the orbits of the other electrons, so it doesn't even see them in a way. Maybe that's a result you remember from 3B. It's like a Faraday cage. If you're inside a shell of electric charge, you don't feel any electric field. But that's a digression here. So Vn squared, I'll just plug it in. Instead of Vn squared here, I'll write 1/n squared, Z squared, K squared, E to the 4th over H bar squared minus. Okay, now I'm going to put this stuff out front. I've got a K, Z, E squared. And then I'm dividing by Rn, which is multiplying by the reciprocal. So I'm just going to multiply by the reciprocal of all this garbage. That's Z M K E squared over N squared H bar squared. So it looks gnarly, but it simplifies really nicely. First, let's cross out anything we can. Does anything cancel here? Doesn't look like it. Same thing here, nothing cancels. Right, right. So do you notice how both terms, they've got a Z squared, see here's Z and Z. They've got a K squared, here's one K, here's the other K. They have an E to the 4th, right? E squared, E squared. They've got an M in the numerator, M in the numerator, N squared, H bar squared downstairs. They're the same thing. The only difference is this has a 1/2 out front, and this has a -1. So it's really, let me put it all together now. Z squared, I'm changing the order slightly. M K squared E to the 4th over N squared H bar squared times 1/2 minus 1. Well, of course, 1/2 minus 1 is -1/2. And now I will do this. I'll say E sub n is -1 over N squared. So what I've done is bring the minus sign out front. And then I'll put everything in parentheses. Z squared M K squared E to the 4th over, don't forget the 2, 1/2 minus 1 is -1/2, so 2N squared H bar squared. I really hope I've done this correctly. If we wanted, we could call this E1, but that only works for, if you actually evaluate Z at 6, an atomic number of 6, and you plug in the mass of the muon, then whatever number you get is only applicable to a muon hydrogen atom with the nucleus of the carbon atom. See, so it kind of depends on the problem, or it does depend on the problem. So what I'd like to do is evaluate this in joules first. We'll plug in everything in SI, then we'll convert to evolts, and then we've got a formula for energy, because all you do for the higher energy levels is just divide down by n squared. So I think I'll demonstrate this whole thing in my calculadora using SI units, and that means I'm going to need the value of h bar in joules. I'm glad I wrote that down. Remember, I put that junk here. Yes, here's the value of h bar in joules seconds. And I goofed here, didn't I? I've got n squared twice. I've already factored out the n squared. Don't need that. Sorry about that. So this doesn't look familiar to me, but again, that's because your book, they like to do it differently. I think they try to extract a Bohr radius in here just so they can write things more succinctly, which is fine. That totally makes sense. But because we're doing something a little different for this problem, I thought this was easier. Oh, last thing we need. We're told in this problem that the muon is 207 times as massive as the electron. So this mass here, right here, is 207 times the electron's mass. So the mass of a muon, I think that's the symbol for muon, is 207 times the mass of an electron. I'm going to try to do this all at once. And I really don't like dealing with denominators and exponents in my calculator. It stresses me out. So I'm going to do the numerator first and take the reciprocal. Or the denominator first and take the reciprocal. So what was the value of h bar? 1.05 times 10 to the negative 34th. I'd square that, multiply by 2. That's the denominator. So I'll take the reciprocal now. Okay, now I multiply by z squared. We're talking about a carbon nucleus with 6 protons, so that's 36, times the mass of the muon, which is 207, times the 9.1 times 10 to the negative 31st that I wrote down. Okay, now I'm going to use 9 billion for k, which is actually approximate. I think it's more like 8.99. I'll just go with that. I think it's 8.99 billion times 10 to the 9th, and I have to square that, times the charge on the electron, which I know is 1.6602, but I'll leave it that way, times 10 to the negative 19th, and I have to raise that to the 4th power. I really hope I did this correctly. Okay, order of magnitude, that doesn't seem too suspicious. Kill another tree here. They grow back. Okay, so 1.63, I'll round it to, times 10 to the negative 14th joules. And you know what? Yeah, that really didn't sound right. I think it should be more like, we're expecting evolts, right? So I was thinking it would be more like 19. But let's just proceed here because I feel like I was careful. Times, well, I want to convert joule seconds into evolt seconds. So 1 evolt, I'm going to do it right this time, is the same as 1.6 times 10 to the negative 19th joules. Okay, so divided by, and you know what? Is it joule seconds or just joules? I'm sorry, it's just joules, not joule seconds. Yeah, this unit that comes out should be energy. Uh-oh. Did I press anything here? I've already forgotten. Okay, I think I hit the division button. So we're good. No, I didn't. 1.63 times 10 to the negative 14th divided by the electron charge. You know what? This does look familiar because I read through the solutions manual. 101,875 evolts. And since I rounded these, I can't keep all these digits. That doesn't really make sense. How about I call it 101,900 evolts? Even that's not really justified. I rounded to this place. Okay, so here we are. The energy of the nth level is negative 1 over n squared times 101,900 eVolts. Now, I am going to pause and check this calculation once more. Miraculously, I got the same number. Evidently, I did that correctly. Okay, so all we have to do now is find the difference between the ground state energy and the number 2 state. I was going to say number 2 excited state, but that makes it sound like it's the second excited state, which would be E3. So I'll just call it the E2 level. So that means E2 minus E1. That's the energy of the photon. Yeah, energy of the photon is the difference in the energy levels as your muon falls back down to its ground state. Well, that's going to be, what I can do is just factor out this. That's negative 1 over 2 squared minus negative 1 over 1 squared times 101,900 eVolts. That seems kind of silly to do it that way, but let's think. Minus minus is plus. We've got 1 minus 1/4, giving us a positive number, which is what we expected because I did the higher energy minus the lower energy. So that's 3/4. 1 minus 1/4 is 3/4 times all this. 101,900 times 3/4, 76,425 eVolts. That's a really big number compared to the hydrogen atom. I hope you've reviewed that for the hydrogen atom, the energy levels are negative 13.6 over n squared. So just a few eVolts of energy in transitions between 2 energy levels. Why is this so much greater? Well, it's because we've got 6 protons in the nucleus, so there's a much greater attraction between the muon and the nucleus, so that it's like a deeper potential well, so to speak. And I think that mass of the muon has something to do with it as well. Now, I'm not talking about this in this video, but you really should. Actually, we could talk about it. Yeah, I'll talk about ionization energy as pertains to this particular atom, because you do need to know about ionization energy and, excuse me, binding energy. Now, I still haven't compared my results to the solutions manual, so let's hope that we're on the same page here. Now that I know the energy of that transition from 2 to 1, I can go back and use the Planck-Einstein relation. Now, I showed you on another page, HF can be rewritten as HC over lambda. Some books actually combine H and C to get a single constant that allows you to easily express the wavelength in nanometers if you happen to know the energy in eVolts. It's just a different system of units that you're using. But since we didn't talk about that, let's just be straightforward about it. And let's use the value of H in eVolt seconds, which remember I pointed out is like eVolts per hertz, eVolts per hertz. And that way we can find the frequency in hertz if we happen to know the energy in eVolts. That's what we calculated, right? I found, I could also do it in terms of joules, but I'd rather use eVolts. So if I solve the Planck-Einstein formula for F is equal to E over H. This pen finally ran out. Give me a moment. The energy we're talking about is 76,000. Probably could have rounded. Divided by, and here's where I will use this value of H. 4.14 times 10 to the negative 15th eVolt seconds. If you're plugging in eVolts, you have to have H expressed in eVolt seconds, not joule seconds. eVolts cancel, and do you see that I have my units of hertz, inverse seconds? And you'll also notice, since we're dividing by an extremely large negative power, we wind up with a very large positive power, which is what we expect. Visible light frequencies or ultraviolet frequencies, they tend to be very high, or not tend to be, they are very high frequencies. 76,425 divided by 4.14 times 10 to the negative 15th. Okay, and I find that the frequency, I'll just do it right here. One more piece of paper, if this works. The frequency of this 2 to 1 transition of the muon orbiting the carbon nucleus is 1.85 all round times 10 to the 19th hertz or inverse seconds. And now we can use the fundamental relation for waves and say that the wavelength of this light is the speed of light divided by the frequency. So that's 3 times 10 to the 8th divided by the frequency. What I'll do is just take the reciprocal of this. This is the reciprocal of frequency times 3 times 10 to the 8th for the speed of light. And I find 1.6. What's with that 1.6 keeps running around? Times 10 to the negative 11th. And I think it would be easier to write that as 16 times 10 to the negative 12th meters, because a trillionth of a meter is called a picometer. Cute little picometer. And that, I believe that's in the X-ray part of the spectrum. As soon as you're talking about picometers, that's shorter even than ultraviolet waves. You're talking about picometers. And now let's get out the solutions. Moment of truth, number 66. What did they find for the wavelength of that transition? I'm a little scared because I really don't want to go back and do all this again. Yes, 1.64 times 10 to the negative 11th meters. Okay, so it's a matter of taste to you, which method you think is easier. We started from the very beginning. Sorry, I should have written meters here. I went all the way back to first principles. We used some results from classical mechanics. We used the notion that the electron is a standing wave which must interfere with itself constructively around the circumference of the atom. And we used some basic results from electrodynamics, namely the force and potential energy of a pair of charges. Beautiful how it all comes together to allow you to correctly predict the spectrum. Now, the last thing I could do is, the problem wasn't asking for this, but what is the ionization energy? And you know what I'll do is a classical result. Those of you who took 3A with me, we like to use this formula from your book, where if you've got a mechanical system, you say that the external work that you do on the system shows up as a change in its energy. So if there is no external work, like or non-conservative work, let's go with that one. And you know, in mechanics, you don't talk about electrical energy, so I'd really have to be more specific about the categories of energy I'm talking about. But any non-conservative work, let's say, would change the total energy. And here I've got two types: kinetic and electric potential energy. Those are the two types that go in here. And let's see, that would be the change in kinetic plus the change in potential. Now, this is counterproductive. I don't need to break it back up into the two types because I already have the expression for the total energy. Remember, the total energy we got by summing the kinetic and potential energies. So let's just say if you've got a particle, this muon carbon atom, let's say, where the muon is in its ground state, and you'd like to take the muon and strip it away from the atom altogether. Remember, that means boosting it up to the E infinity state. These just stack up closer and closer together. To get your, remember the radius looks something like this, n squared times some garbage in the parentheses. To get your muon infinitely far from the atom, in other words, to ionize it, and it's kind of a weird problem because normally ionization means removing the outermost electron. Now we're talking about this inner muon. So let's not worry about the details there. But to get this out to infinity, give it a quantum number of infinity. So you need to boost it from the E1 to the E infinite level. That's how much work you have to dump in from the outside. Well, E infinite, if you go back to the formula for each energy level, yeah, see, this is where my organizational skills are suffering. Yeah. For E infinite, you would plug in n equals infinity, 1 over infinity squared. Well, that's 0. So it's really just it's 0. 0 is the total energy of the highest state. And remember, that's like, I'm probably making you dizzy with all this paper shuffling, but the total energy looks a little bit like this. And we're making these discrete jumps. It's a lot like the potential energy of gravitational orbits in physics 3A. And we're just getting closer and closer to that highest possible energy, which is actually 0. Don't be hung up on the fact that all these energies are negative. That just refers, that's related to the fact that the orbits are bound orbits, just like in 3A. If a planet is stuck moving around the sun, if it's not going to escape, it's got a total energy that's negative. Okay, minus E1. And didn't we find that E1 was however many thousands of eVolts? I'm almost done here. Don't worry, I'm irritated too. Yeah, so hey, take a hint from me. If you have a problem like this on your exam, maybe you set your pages all out in some organized fashion. And anyway, I forgot what the number was. Wasn't it like 76,000 eVolts? Here it is. Yes, 101,900. Negative 101,000. Yeah, E1, remember, is a negative number. 101,900 eVolts. So it's kind of an easy answer. It's just the negative of the ground state energy. The ground state energy is negative 101,900 eVolts. So the ionization energy is just the opposite of that. Much larger than the 13.6 eVolts for the hydrogen atom. I really hope you've read about that. A photon, if you had a particle in a really high excited state of the hydrogen atom and fall all the way back down to the ground state, it loses about 13.6 eVolts. And if all that energy goes into a photon, that produces an ultraviolet photon. Your eyeball cannot detect a 13.6 eVolt photon. 2 to 3 eVolts is the range of energies for visible photons. So I haven't talked about that in this video, but you really need to be aware, familiar with the Bohr model of the atom generally. Not just the hydrogen atom, but the Bohr model of the atom, where electrons transition between energy levels, and the difference in the energies equals the energy of the absorbed or emitted photon. Because on your exam, you may have to calculate wavelengths for certain transitions. I didn't emphasize that aspect in this video, but it's fairly easy compared to what we did here. So you are responsible for knowing that. Review the particle in a box. That's much more straightforward than what we've done here. You don't need to do Compton scattering. What was the other thing? The photoelectric effect. You will have a problem about the photoelectric effect. And that's it. So we got to dip our feet a little bit in modern physics. The story gets much more interesting as you continue. So it's a shame that we don't have 4 semesters to do all this stuff. 3 is really not enough. We took a lot of time for thermodynamics, did we not? And the first chapter or 2 of thermodynamics, you were probably thinking, this is a waste of time. I already know what a mole is. I learned this in chemistry. But I really hope that by the time we got to heat engines, you realized that it was worthwhile, that physics classes do have something else to offer when it comes to thermodynamics. Now you hopefully have some sense about the second law of thermodynamics, reversibility of an engine. And if you're going to major in physics, you'll be glad that you learned all that stuff. Okay, good night.